All right. Good morning, everyone. So here we begin our third day of conferences about data analytics and speed data. So here today we will. I'm very happy to welcome Qiwei Yao from London School of Economics. We will talk about dimensional modeling of time series, and especially forecasting based on time series PCA. So thank you, Qiwei, to be here. Enjoy the talk.
Good morning, everyone. Many thanks for Yannick to invite me here. I understand that this is a workshop very much related to the energy data. My apologies first. What I'm going to present is not directly directed on energy data yet, but the ambition is we will start a joint project with Yannick and his group to apply some of those things and develop further for the curve electricity demand data. Okay, so this is joint work with a couple of people, and Jingyuan Chang and Bing Guo, they are from the SUFE in Chengdu, and my colleague Xinghao Chao from London School of Economics. The title says it's multiple forecasting based on time series PCA. The reason I present this talk is the following. Okay, so when we talk about time series forecasting, and especially if we talk about multiple or large number of time series forecasting, the conventional wisdom says you are better off to forecast each time series separately. Just ignore, don't bother with the cross correlations, because if you use a vector model for say for 10-dimensional time series, the gain from the cross autocorrelation or cross lagged correlation will be cancelled off by an estimation errors. The reason for that is the multiple time series model, even say simplest autoregressive vector model with order 1. If we are talking about 10 time series, the coefficient is a 10 times 10 matrix. You need to estimate 100 parameters. So estimation error just overwhelm the gain by looking at the cross correlations. So this is why in practice, when we talk about forecasting multiple time series, you see people typically try to do it one by one. What do we try to propose here is say, okay, perhaps we should do some transformation first, such that after transformations, those transformed time series can be forecasted separately. And the first thing you come to mind is the principal component analysis. But the trouble with the principal component analysis is it's only deal with the correlation at the same time. When we look at time series data, the correlation occur at the same times, also across different time lags. So that's what we say we need a version of time series PCA. Before I tell you what it is, there is a package in the available from the Crown package called PCA for time series. Yeah. Okay, here's the outline. What do we try to do? First, we talk about, let's say, high dimensional time series. That means, okay, a high dimensional means 10 or 20 or 30. Yeah? 30 time series. What do we try to do? Is we try to do a transformation, transform, say, 30 time series into new 30 time series. Ideally, those new 30 time series are uncorrelated at the same time and close all time lags. So this is what we try to do. Because if we say those time series are uncorrelated across all time lags, there is really no point to forecast them together or model them together, as far as the linear dependence structure is concerned. So that's what we try to do. And the methodology we propose, as I said, is a time series for PCA. And technically, it's just like the standard PCA. you do an argon analysis for a positive definite matrix. In the standard PCA, it's covariance matrix. But in time series context, it should be something more complex because it should also capture the auto-dependence, the dependence across different time lags. But still, technically, it's argon analysis for a positive definite matrix. The complication is second part, the permutation. If we are dealing with, say, a small number of time series, say 10, probably we can get away with that because you can look at the parallelogram of 10 time series, 10 times 10. If you're familiar with the time series, that's 100 panel of correlation plot. Yeah, you look at those 100 panel, then you can figure out which are correlated with each other. But if it's sort of higher than 10, then we have too many panels to look at. We need some analytical method. Why is that? The reason is, unlike PCA, standard PCA, you're given a vector time series, I can always find a linear transformation. After transformation, those random variable are uncorrelated. But now we are asked for more. We ask for uncorrelation across different time lags. Unfortunately, this is not guaranteed. And sometimes after transformation, say 10-dimensional time series, after transformation, you transform them into 7 subtime series. Some are univariate, some has more than one time series. Yeah, because correlation is still there. So you have to deal with the sort of small vector time series together. This makes the sorting more complicated. That's why we need a permutation. I will show you quite a few real data illustrations. And then, if time permits, I will also talk about how to extend this idea for the multiple volatility process. Do a transformation. After transformation, the multiple volatility process become uncorrelated. This is the conditional uncorrelated. Yeah. And we also going to talk about bundles of curve time series. This is something I and Yali are thinking to apply to the smart data, because once we have a smart meter data, we have lots of like daily consumptions of each household. So time series become a curve time series for each household. You look at the daily expenditure over the time. You have one time series. You have many times households. So you have many curve time series. This is what we call a bundle of curve time series. What we try to do is that we apply transformation, transform them into a new bundle of time series, curve series. Those new bundle of curve series are uncorrelated. Yeah, we can do forecasting separate. So this is what we try to do. Do stop me if anything is sort of unclear. Yeah. So this is what we try to achieve. We have a p-dimensional weakly stationary time series. That means the mean value is constant. Covariance is independent of time, only depends on the lag between two variables. Then what we try to do is to find a linear transformation, say transform y to x. The transformation matrix is A, or you write the other way around, x equals by, such that after transformation, x is still p-dimensional time series, but it can be segmented into Q subseries. And those subseries are uncorrelated across all time lags. So if we can do that, then those subseries can be modeled or forecast separately as far as linear dependence is concerned. Okay, I guess the first two questions, is this a realistic assumption? Given multiple time series, can we find such a transformation? If even say such transformation exists, how to find the A and B? So those are two questions we need to answer. But before I answer those questions, let's look at one example, real data. So this is all data I used for quite a while in a few papers. I like this data because this is almost my almost my birthplace, and this is where I did my university education. Yeah, and you know this Shanghai. So between Shanghai and Nanjing, there are 300 kilometers distance. So this is just a small part of China. So we look at the monthly temperature in this time period. And the data I got it from teaching a class in Beijing. A student gave me this data. Actually, the real data set is much bigger. It has the temperature over 400 cities in China, daily temperature, yeah, which sort of take a subset of this. So this is so 7 city times 50 data. Of course, you can see monthly data. There is a strong seasonality with period 12. But this is annual period. If you look at the cross correlation, this is 7 times series. There are 7 times 7, 49 panels. On the main diagonal, like here, this is the autocorrelation of the first subseries. So the 2-2 place is the autocorrelation of the second series. 1-2 position and 2-1. Those are cross correlation between first and second series because they are not symmetric. Yeah, one is sort of one series 1 lagged series 2. This is one is delagged by series 2. That's why for the cross correlation you need 2 panels. For the series itself, autocorrelation just need 1 panel. 7 series, you have the 49 panels. What you can see is this autocorrelation are dominated by the seasonality. There's a strong seasonal variation with period 12. Okay, now apply transformation. For the time being, just take it, say this is a transformation apply. That's 7 times 7 matrix. After transformation, what you can see, the first one is really like PCA. Yeah, take a mean value of 7 series. You see a strong seasonality. Second one, seasonality is still there. Third, fourth, and so on and so forth become sort of less influenced by seasonality. So those are transformed new 7 time series. And you look at the autocorrelation of those transformed series. Now you can see seasonality are still dominated by first and second components. And as I said, off-man diagonal are cross correlation between the series. So if you zoom in, you can see closely, like here. There are some significant but small correlation between, in this is a 2-3 place, the second series and third series. So if you want to group those new 7 time series into groups such that there are no cross correlation between groups, you should put 1, 2, 3 together because there are correlations. And if you look at others, there are hardly any correlations across different time lengths. So this linear transformation transforms a 7 highly correlated series into 1, 2, 3, 4, 5 groups. And 4 are univariate time series, 1 is 3-dimensional time series. So when we do forecasting, we can forecast those 5 subseries separately. Because transformation is 1-to-1. Once you forecast those new series, apply the inverse transformation, you get the forecast for original time series. So that's the idea to see. So this is the post-sample forecasting. So we have this series, we apply transformation, get X. Then what we do is we forecast. We do a genuine post-sample forecasting. Leave last 2-year data out as testing sample. And for each of those 24 values, we use the data before to fit, because now we try to compare them. We don't do any fine tuning, just fit each of them as a vector AR model, order determined by AIC. No any subjective tuning. What we do is, okay, we compare with the vector AR. So we fit the 7 times original time series together. That's one approach, VAR. RVAR is this called a restricted VAR. Once you fit the vector time series, because as I said, the coefficient matrix is, in this case, is 7 times 7 matrix, 49 coefficients. There are many coefficients are insignificant. For insignificant coefficients, you can set them as 0. You get a better fitting at this. So this is done automatically in a package called a VAR. VAR allow you to fit a vector AR model and a restricted vector AR model. So we do that for each last 24 values using the series beforehand, fit the AR model, then forecast next value, and we do further two-step forecasting. Just plug in, forecast one value, plug in, you forecast another value. So you have one-step forecast, two-step forecast. You do that for each of those 7 cities. You have the mean square error of your forecast, and in the brackets is the standard error of your forecast. The last is using the time series PCA, 5 groups, do the forecasting for the new series X, then transform back to original Y. You can see the performance is improved by this transform-based forecasting. So this gives you an idea what we try to do. Any questions?
I have a question. So you restrict yourself to first order dependencies, right? Among the series? Or?
No. You just take a series, fit a vector AR model. The order is determined by AIC.
Okay, so here, okay.
Yeah. You always pick the order.
All right.
Picked by the AIC. Yeah, we don't do any kind of subjective tuning.
Okay.
Yes.
So how is it that the 2-step ahead prediction is better than the 1-step ahead prediction?
This is very much depends on, because the data are sort of, there is strong sort of seasonalities. Some season is much better to predict than others. You do have this kind of strange things. Yeah.
Well, I have a more kind of general question, because you applied everything to this temperature data set where you have a strong seasonality that you mentioned. But at the beginning you had the assumption that you have basically a weakly stationary series, and this is not the case for the series because you have the seasonality. I think you should remove first the seasonality and then apply your method.
I think your point is valid. There are 2 answers. Probably we didn't remove the seasonality, that's 1. 2, seasonality can be accommodated in the weekly stationary model. We can do that.
Well, but if you have a stationary process, the long-term mean is constant. So if you have a very long-term forecast, it's just flat.
No, so what do you do? You can. No, I'm not saying we are using it. As I said, probably I need to check. Probably we remove the seasonality when we do the forecast, do the modeling. Yeah. But if really for the sake of argument, say you want to accommodate the seasonality component, you just put a harmonic component. Okay. Now let's see how we try to find this transformation A and B. So this is just recap what we try to do. We have Y, we apply transformation A, and after transformation, X can be segmented into subseries. And when you look at this transformation, we only know Y, we don't know A, we don't know X. So there is a free condition we can impose. We say X has a covariance matrix identity because you can absorb the covariance matrix into A. That's condition 3. Then we observe the Y. We can use the sample covariance matrix, do a standardization first to assume the variance of Y is also an identity matrix. Why we do that? With those 2 conditions, the transformation matrix we are looking for is an orthogonal matrix. Actually, this is kind of standard trick for the independent component analysis. They always do principal component first, yeah. Then you go forward. So A is the identity matrix. But still, you look further. these AX are not fully identifiable. Because if A is correct, that means you find each segment of X. Within segment, you can rotate. You can rotate each small x. This will not alter the factor. It is uncorrelated with other components. So what I'm saying is, if A is right, you can replace A by AH. H is a diagonal orthogonal matrix. Each small h is a small orthogonal matrix, and you put it in diagonal form, then AH is still orthogonal. So AH is as good as A. So what we are really trying to identify is the column spanned by each A matrix. This linear subspace is identifiable by the nature of the column, not the A itself. So, subject to the notation, orthogonal transformation, this A is identified. Okay. Now, I introduce some notations. Sigma yk is the covariance matrix of y at k, which we observe y, we can estimate it. And corresponding to that, we have a covariance matrix of x at leg k, which we don't observe. Yeah? But we know x has this segmentation. Each components are uncorrelated. So what we have is sigma xk is also a block diagonal matrix. This is important. Yeah? Because of uncorrelation among different blocks. Okay. Now we try to accumulate the information over different time lengths. So what do? We add sigma yk times transpose. Then this becomes a semi-definite, positive semi-definite matrix. It's much easier to handle. Yeah. Then we add them from leg 0 to leg k naught. You accumulate information over different time lengths. You do it for y, called wy. You do it for x, called wx. Important thing about wx is it's a block diagonal matrix. Because each sigma xk is block diagonal. This is important. Okay, because we assume that A is an orthogonal matrix. So if you replace the sigma yk here by the sandwich equation, sigma yk equal A times sigma xk A transpose. So sigma y give you a A transpose in the back. Sigma y transpose give you an A in the front. This A transpose A cancel off. So that's why we have this sandwich formula also applied to wy, wx. And this gives us the way to find the transformation matrix. Okay, so what do? As I said, technically it's eigenanalysis. We do eigenanalysis for wx matrix, which is a positive definite matrix. Yeah, eigenanalysis can be performed easily. So typically you write this matrix times eigenvector equal eigenvalue times eigenvector. So if you write those all eigenvectors into an orthogonal matrix, yeah, so gamma x, the column are eigenvectors. Then wx times gamma x equal gamma x times diagonal matrix of eigenvalue. This is the eigenequation. Just one equation. Write all p eigenvalue, eigenvector together. So this is eigenequation. Okay, and once we have that, you can see there is a clear relationship between the eigenvector of wx and wy. Why? You do wy times a gamma x. Remember, wy equal a sigma xk, sorry, wy equal a wx a transpose. Plug in. This a transpose a cancel off. What you have is a wx gamma x, like this. So, because the equation we have, wx gamma x equal gamma x d, you replace this. Ignore the middle part. Look from here to here. You can see this a gamma x actually is eigenvectors of wy. Okay, so this is concluded. Our eigenvector of wx actually is a transformed eigenvector of y. The transformation matrix is exactly the A we are looking for. Now, this is like kind of invariance property. Gamma y times yt, this part is observable. We can observe, yeah? Equal to gamma x transpose of xt. This part we don't observe. We try to looking for. Okay. Now, we are saying, actually, this equal to this. This is as good as x we are looking for. Why is that? Because wx is a block diagonal matrix. Each block is a small positive definite matrix. So you can apply eigenanalysis to each small blocks. So you end with a small orthogonal matrix with diagonal matrix. Line up all those small orthogonal matrices into a block diagonal matrix. It's a big orthogonal block diagonal matrix. What I'm saying is this can be taken as a block diagonal matrix. Block diagonal matrix times to xt is exactly what I said earlier. Once you find x, you can rotate each subseries of x. This will not alter the fact that there's no cross dependence among different blocks. So we are done. Yt observable, this can be estimated, and this is what we are looking for, the transform of xt. And this is our transformation matrix. Sounds good, but actually there's a catch. What we are saying is Zt, which is gamma y transpose y, is a required transformation up to permutation. The problem is this block diagonal structure of wx or gamma x is hidden. When you apply eigenanalysis, the output do not line up the eigenvector in those nice block diagonal structure. It's up to you to see how to arrange them, rearrange them to recover this block diagonal structure. So this is the catch. As I said, if dimension is lower, you just look at the cross correlation plot. You can identify who and who are correlated. Well, if it's bigger, then we need to do some analytical analysis. Any questions?
How do you decide on this K0 when you do the computation?
Yeah, that's a good question. I will come back to this point later.
Okay.
But I can intuitively, we are dealing with time series. The dependence typically occur in the first few time lags. If the dependence is strong, even say you don't have all possible information, you catch a few lags, it will do. Yeah. Okay. So we try to summarize what we said. Okay. Gamma x can be taken with the same block diagonal structure as wx, which we don't know. Any gamma x is a column permutation of gamma x described with this structure. Provide the eigenvalue for different blocks are different. Because if you have the same eigenvalue, you cannot distinguish the eigenvector space. So this eigenvalue just corresponds to a two-dimensional space. We don't know which one direction to go. So we need to have an eigen gap between the different blocks. Okay. So in practice, what we do, you replace the sample covariance matrix Y, the autocovariance matrix Y by sample version. You have a version of WY, then you apply the eigenanalysis, you have a gamma Y. And the gamma Y transpose Y is what's required. X up to a permutation. You still need to change the order of components to put the dependence together. So, permutations. The principle is simple, how to do the permutations. So what do? We define, say, that any two components are connected if the multiple non-hypotheses, say, the close correlation between those two components at lag k, for k between minus m to m is 0. This multiple non-hypothesis is rejected. We say those pairs are connected. So you have p-time series, you need to do a lot of multiple hypothesis testing. Actually, we are not doing that. We try to get sort of quick, dirty way out. But in principle, this is how we decide whether two components are connected. So permutation performed like this. Start with p groups, each containing one component. Then we combine two groups together if one connected pair are split over two groups. You continue until all connected pairs are within one group. So that's the permutation we perform. Okay, so what do we do? The first procedure we do is to look at the maximum cross correlation. You have two components I and j. At lag h, correlation is rho I j h hat. Then you look at the maximum value, absolute maximum value. You take this Lij as the statistics, reject h naught for this pair for larger value of this. So intuitively it's clear, but the question is how large is large? What we do is we not really do a testing. What we do? We rank the dependence. The largest come first. Those are most correlated pair. And you do this ranking in the descending order. In total, there's p times p minus 1 divided by 2. You look at the ratio. Lj hat over Lj plus 1. So, suppose there is one connected pair, you start with something non-zero. Suppose there are unconnected pair, the minimum true value should be 0. When you go down, it's non-zero, non-zero. At one point, it's non-zero over 0. So this is maximum. Yeah, this is the value you're looking for. Okay. So this is sort of quick and dirty procedure. What's the time?
It's here.
I should stop in 20 minutes, something like that.
Yeah.
Okay.
We can.
Okay. I skipped this one. So what's important here, as I said, is this condition. You need to create an eigen gap. This one. This is the gap between eigenvalues in different blocks. You can see, finally, the condition require the convergence, the estimation error over this eigen gap should go to 0. This is the crucial condition. Yeah. Under this condition, the procedure we described before will converge to the true. Yeah. When you do time series, there's lots of sort of small traps. If you don't take care, you are sort of trapped. This is another one. What happened is we are basically looking at the correlation, cross correlation over different pairs. If you look at the asymptotic distribution, the variance of the correlation depends on the autocorrelations of two time series concerned. Therefore, we are in the danger to compare apple with banana, because if the two pairs have different variance, one variance is bigger, one variance is small, you look at whether the mean value is 0, look at asymptotic distribution, and the independent condition, mean value is 0. So basically, you compare normal distribution with mean value 0, 1, and normal distribution with mean value 1, 1, and normal distribution with mean value 0, variance 10. Yeah? So which one is smaller? Mean value? Probably you will see, okay, 1, 1 is smaller because of difference in variance. So what you need to do is to standardize it such that to make sure all those statistics you look for have the same variance. Then look at which mean value is non-zero, makes sense. Which mean value is bigger, makes sense. What we do is we need to apply an older trick, which is pre-whitening. Pre-whitening. Make sure each transformed series is white noise. How to do that? You just fit AR model and look at the residual. Because if there's close dependence, the dependence will represented by the residual in the process. Those are equivalents. So this is a pre-whitening. You fit each transformed time series with AR model, and order selected by AIC. We just don't want to order too high to fit out all the dependent structure. So arbitrarily, we set the maximum order is 5. Because for finite data, if you fit too much, you just fit AR model with order too high, you just fill out all the dependent structure. There is multiple testing, which is based on FDR, force discovery rate. We need to do it twice because for each pair, we need to look at the lag from M to M. Then we need to look at the different pairs. So this is 2 times multiple tests. Yeah, there is a way to do that with it hands waving. I skip that for the interest of time. Okay, let's look at some other data. You may realize we have quite a few tuning parameters there. As you mentioned, the lag of time. When we do the testing, this minus M to M, M is another tuning parameters. Then how to handle those things? What we are trying to say is actually it's not so important how to choose tuning parameters because it's basically down to how much dependence you take into account in your forecasting. That's one issue. Another issue is that I haven't said anything about say if there's no such transformation. Doesn't matter how you transform. After transformation, there are still cross dependence. Yeah. When you apply this procedure, what do you get? Yeah. I will show you some examples and which will illustrate how we deal with those issues. This is another data I use quite often. Monthly US industry production indices. And there are 8 indices. It's non-stationary data with trend because the economic growth, so the index always go up. So either way to handle it is just like a linear trend. You take a difference series, you take a difference, then you calculate the difference, the monthly index. So 8, there are 84 panels here. When you look, you can see there are cross correlation everywhere. Yeah, cross correlation like one last series is correlated with all series. So if you don't do any transformation, clearly all those different branch industry indexes are correlated with each other. And you do a transformation. This is transformation according to our procedure. And this is transform the data. This is after transformation. With 8 series, you still can zoom in, looking for the small but significant dependence. The segmentation have 1, 2, 3 should be together, 4 and 8 should be together, 5, 6, 7 should be together. So we end with 5 groups. And this is by looking at by eyes. If you apply the maximum correlation procedure or the FDR, you get slightly different grouping, yeah? Which seems irritating, but later I try to convince you, doesn't matter too much, yeah? So put them all together, there are different way to do the segmentation. One is that 7 groups, just put 1, 3 together, all other on its own. 5 groups, 1, 2, 3 together, 4, 8 together, all other on its own. This is kind of vision detection. We apply the same trick as before. Fit each time series with vector AR, order determined by AIC, without any tuning. And this is the 1-step, 2-step post-sample forecasting. You can see it's time series PCA still give you a slightly better forecasting than without transformations. Okay, I should really speed up. Sorry. Weekly MESO data. Is this the one? Don't have. Yeah, that's the one. Okay. This is the data show you the transformation failed. Even after transformation, there's still significant correlation between the transformed data. Okay, those are weekly notified MESO cases in 7 cities in London, Bristol, and so on. Why data stopped at 65? Because after that, the fascination became compulsory. So dynamics completely changed. This is typical biannual data. You have 1 year which has lots of measles and lots of medicine has been applied. So the virus is suppressed. So next year is small. Then next year is small, the virus come back. So it's always kind of biannual circle. And this is the correlation before the transformation. And this is the transformation according to our procedure. This is transformed series. This is transformation, this is autocorrelation after transformation. You can see the correlation everywhere. And pre-whitening still doesn't make the things much better, because if you look at the correlation analytically, so this is what we do. We have 7 cities, we have 21 pairs. We can calculate the maximum correlation for each pair between lag of -20 to 20. So you have a maximum correlation for each pair of cities. You plot them in a descending order. This is the maximum correlation, yeah? Second maximum, third maximum. So without any test, you can say, oh, first few shouldn't be 0, yeah? Ignore the second plot. So what it does is, now you can cut. So if I only accept first one is non-zero, what it implies is that I divide the 7 transformed time series into 6 groups. Only one group will have 2. So if I go say I accept the first 2, then it's 5 groups. I accept 3, it's 4 groups. You only need 6 non-zero correlation to put 7 cities together. The previous slides show first a few more than 6 are non-zero. So in this case, the transformation doesn't work. But still, this kind of ordering is interesting. Basically, you order the pair according to the strength of dependence. If you take first 3, you just ignore the still significant, a small correlation. So this is post-sample forecasting. And univariate, if you don't do any transformation, using vector series, and using distributed vector AR, distributed vector AR. Then, now you have a choice. You do a transformation, you take the 4 groups, 7 groups, 3 groups. Of course, the results is different. It turns out, in this case, 4 groups is the best, but still, even say 7 groups, 7 is original number of cities. Yeah, you original 7 time series. You do a univariate forecasting. You do a transformation. You still do a univariate forecasting. You can see after transformation is better. Yeah, after transformation. So transformation is always makes forecasting better. You may wonder why. We will give a reason why transformation is always better later. Okay. Sales of the close brand in 25 provinces. This is time series with P equal 25. And again, this is I give a course somewhere. A student give me the data, yeah, in audience. So I will have this data. Would you like to have it? I said yes. And it's we can see. I'll go through it quickly.
I think actually you have to spend more time if you want.
That's very bad. That's very bad. I try to stay within my time. Okay, this is the 25 time series. You do a univariate forecasting, and you do a vector AR, restricted vector AR. As I said before, the common wisdom tells you, don't bother with vector model. You do a univariate AR with original series, you are better off. Yeah? But if you do a time series PCA and group, it's not unique, but you can use cell 24 group or 25 group or 23 groups. You can see it's significantly better than without transformation.
So how many series do you have here?
25. 25 series.
Did you try to compare with just the standard PCA precision?
Our standard PCA, we didn't, but standard PCA ignore the dependence.
Yes, of course I know, but I like to see, say, the difference between.
You see, this is something which has been heavily used in time series literature, and for lots of applications, standard PCA works fine because it happens the principal components direction is also the direction has a strong dependence structure. In this case, it's fine, and if say the dependence direction is different from principal component, it's easy to construct such a simulation example because you just make the innovation have a different variance. It will shift to the principal component direction from the dependent structure. Then the standard principal components fail better. Yeah. I have students ask me this repeatedly. In the end, I said, run simulation, use innovation with different variance. One is 1, one is 10. Of course, PCA is completely off the track. This is PM25 in China. I skip this one. Okay. We tried with various real data example, and honestly, it's always PCA transformation is better. Why? Here is the reason why. As you know, everything is hinged on this sandwich formula. Wy, Wx related with each other with this orthogonal transformation. And if you calculate the trace Wy, it's just the correlation, autocorrelation, cross correlation over different leg squared together. So what we try to say is if you do a linear forecasting, this trace Wy is a measure for the predictability because your forecasting for the future depends on the autocorrelation. That's all information is useful for forecasting. Wy equal A transpose A Wx A transpose. Therefore, you swap the order A transpose cancel. So Wy equal trace Wy equal trace Wx. By the same token, this is the auto cross correlation of all components X. So that means when you do the transformation, you didn't lose any information. Now think this way. Suppose that we are working with ideal situation, X are uncorrelated That means the row I, j for I not equal to j are all 0. So what this transformation does is to push all correlations over different time lags into a few directions. Makes those directions more predictable than others. You don't need to bother with the cross correlation. Cross correlation is difficult to catch in the forecasting. So that's why this makes things forecasting better. When the transformation doesn't exist in the sense you transform it, still there is dependence. What it does is to ignore the small but still significant correlation. That's why typically you still have a better forecasting. Yes. Skip the volatility since Nick is interested in the curve. Okay. Actually, this procedure applies to the bundle of the curve time series. So this is what we have. The Y is a bundle of curve time series at P curve time series, Y1, YP. They're defined on the interval I. Okay. What we are looking for is looking for a P times P orthogonal matrix. So change this bundle into X. Yeah? And ideally, say those transformed time series are uncorrelated. So now you can calculate a P times P covariance, P times P autocovariance matrix of X bundles with fixed U1, U2. Fixed U1, U2. Because fixed U, U is fixed. This X become a vector, P vectors. Yeah? So fixed U1, fixed U2, you have two vectors. You calculate the cross covariance, it's a P times P matrix. So in this case, if their curve series are uncorrelated, this is the diagonal matrix. Therefore, this sandwich property still holds because A is, as we said before. Once we have that, we can accumulate the information over the curve. You do integration. WY, WZ, YWZ should be WX, sorry. WX, you just do accumulation. Then we have exactly the same property as before. So the trick we played before, we apply to here. And you can, I didn't mention the theory, you can prove some asymptotic series, and you can even let P goes to infinity together with N and so on and so forth. First part of paper is published already towards the end of last year in Annals of Statistics, and second part we are still working on it. One thing we didn't address properly is really when P is large. When P is larger, estimation of covariance matrix need to be modified. There are tricks which works fine in theory, but in practice it's still challenging. The software we implemented, we didn't tune the covariance matrix. We just used a sample version of covariance matrix. And so far I said, okay, this approach is nice, fine, but as you can see, probably the largest dimension I use is 25. If you really talk about dimension 100, 200, you have to deal with the estimation of large covariance matrix. And it's not, say, practically, all those methods works less ideal than theory tell you. I guess probably we need something else. Like say, we're trying to use the idea like random forest. You take a small subset, do the forecasting, then do it repeatedly. And eventually you accumulate the estimation together. I think this way is much better than to estimate, say, a 200 times 200 covariance matrix directly. So I stop here. Thank you very much. Thank you.
So concerning, the big data case where you have 1,000 series, or so, do you think we could think about a distributed strategy, like doing some cluster in a dirty way, and then estimate the principal component in each cluster, and then conciliate the results.
Yeah, I think if I understood you correctly, this is sort of in the same spirit as I mentioned. You look at the subsets, randomly sample subsets,
Okay.
do the forecasting, then accumulates the results eventually. It's one guy ran some simulation. It seems working fine, very encouraging, but we were stopped because we couldn't prove a secret.
And maybe another point is if we think about so every example you showed, you have time series that are the same resolution, temperature or closest. And do you think we could adapt the method to a hierarchical structure, like on the electricity network? You have time series at different hierarchy with different signal to noise ratio. So I think what you said about the preprocessing of variance, etc., should be interesting also to see in that case.
I think different signal noise ratio is okay, but the different scale, I don't know if they are not so observed on the.
But you see, the application is really interesting for electricity because it's really hard to forecast a smart meter, one smart meter or even a small group.
Yeah.
But if you use a correlation, I don't know, with regional electricity or national one, which is more predictable, maybe you have you can gain forecasting performances that way.
So I see also many applications, especially in electricity price forecasting. We, at least in Europe, we have naturally usually 24-dimensional or 48-dimensional time series, because every day we have an option for the next day's electricity prices and hourly product. And there are a couple of procedures. Well, we have this kind of standard PCA then, and then afterwards do the backward regressive on these kind of things. And they perform quite well, not perfect, but but this were outperformed in the past by just using univariate time series modeling, by plugging in all the cross correlation things, and then just using high dimensional methods, some lasso type things. And this performed at least better, but maybe these kind of things are here better than what we did so far in the past in this area.
As I said, in practice, standard PCA has been extensively used and typically produce a sensible, usable result. I can understand why, if the innovation or noise across different series are really not dominating, the PCA probably is okay, you can catch the dependent structure. But whether this procedure will perform better or not, I don't know. We really need to choose.
It's a good idea for this area at least. I think so.
You see, at least in terms of time series thinking, to catch the dependence in your modeling is a natural way to do it. That's what we try to do.
Some question. So you need to select some component, right? So at some point you should cut maybe. So when you do your decomposition, you have all the components, and what you need, you groups them, and you have to cut somewhere. So
No, we don't cut.
So you showed in your table.
Oh, you mean the dependence? Yeah,
Yes,
that's
right.
right.
That's right.
That's right.
Is it possible to do it in a smooth way? Like the analogy I want to make is principal component regression and ridge regression, which are related, but one just cut the component and the other penalized the component. Can we make an analogy here in your table where we can have a parameters that control the groupings?
Yeah, I didn't think this way. But where to cut is basically how many groups you use in your final result. As I show you, you use different number of groups and you get a slightly different performance. But still, the transformation is better than without transformation. Because basically, you Doesn't matter which way you use, the maximum correlation or FDR. You rank the pair according to the strength of the correlation. So when you cut, you just leave out those at the tail. How many you left in the tail is depend on how much where you cut in the table. That's basically what it does.
What do you think we can do if the dependent structures is non-stationary? It changes in time.
Yeah, okay. That's a very good question. I guess when you have the non-stationary time series and multiple non-stationary time series, first thing I would think is co-integration. And when you do the forecasting, I always believe you can always forecast based on some stationary properties. Even say original data is not stationary, you need to looking for kind of stationary properties. For the electricity demand, there are lots of co-integrations there. I would think first extract the co-integration components, deal with that using the error correction model or whatever. Then rest is stationary components. You can apply the conventional time series approach. Again, the argon analysis is a good way to do co-integration. It has been used in the co-integration literature, but not as much as it deserves. People are typically looking for something else, which is much, much less effective. Because I think the argon analysis is really sort of economic way to extract the information in a sort of very compact format. For the co-integration, for the unit test, argon analysis should play much, much bigger role than what it has been played. Yes.
You didn't have time to talk about the volatility part, but I was
Yes.
quite curious about that. Could you maybe just briefly say, would you essentially apply it to the residuals, or would you look at realized volatility measures? And
No, I didn't look into realized
Yeah.
volatility. Where is it? Okay, so basically you have a p-dimensional volatility process. The volatility matrix is a conditional matrix. What we are looking for is looking for a transformation. After transformation, this X, the covariance matrix become a block diagonal matrix like before. But now we are talking about conditional variance. So what you need to do is to transform this conditional block structure into something unconditional. Because we know if they are conditional independent, it's equivalent to say this times this pi set. This is pi set. If it's sigma algebra generated by this pi set equal to the ft minus 1, then this property is equivalent. Nice thing about this is it's unconditional condition. We just transform this conditional requirement into this unconditional one. Then you build a sandwich formula as before. Then it's done. It's in the paper published in Annals. Yeah, a few pages. We didn't fully develop it. We just outlined how it can be done, and we even have one example.
When you look at several time series simultaneously, you can have different kind of relationships between time series. What you look at is the correlations, and you make them independent by your transformation. But you can also assume a relationship which is, say, that the order of the AR is the same for each time series, or the coefficients look similar, or something like this. Do you think possible to combine your work with some kind of multitask approach using this kind of information?
You are, if I understand it correctly, you are talking about say, if we have a model for X and Y, or for Y, whether we can take advantage of this explicit formula of model. You see, this is something to do with, depending on what you want to do. If you want to do a forecasting, the model itself is not important if you do linear forecasting. It is hinged on autocorrelation. If you want to do a modeling, interesting question, but I don't see it through in my head right now.
Well, just in terms of the examples you showed for the temperature in cities in China, you can assume that similar kind of forecast will work for all cities. Or maybe there will be two blocks depending on the climate. And if you know that you should select the same AR order for having a good forecast for all cities, right? This is an information that can improve your
I
forecast.
understand.
So this is the kind of information, maybe not a strong model, but some prior information. I was
We
wondering.
didn't look into that purposely because we tried to do a fair comparison without any subjective tuning.
Yeah, if we think about the electrical setting, what I have in mind is maybe a two-step strategy because often there is a lot of dependency to covariates of electricity. So you need first mid-term model to estimate those effects, and then work on the residuals. But sure, maybe there is the properties of the different model you use. That this first step could be maybe used for the second step of correlation modeling.
Yeah, I think in real forecasting, nobody will apply what we did here, just blindly apply the procedure without using any subjective knowledge. And when we sort of first position this procedure, we try to sell it as a kind of preliminary data analysis for time series. If you have multiple time series, do a transformation, reduce the dimensionality, then you move forward.